want to talk you through an algorithm that runs on networks. So here's a diagram of a particular network, and you can see that it's basically made up of blobs, which we call nodes, and lines, which we call links or edges. So the network is a fundamental structure in computer science, and you will encounter and make use of them a lot. Now, if we think about this basic structure, things being connected in some way, what sort of networks do you encounter in your everyday life? So what I'd like you to do is just pause the movie for a moment and have a think about the types of networks that you see and encounter in your everyday life. When you've had a think about that, restart the movie. Well, networks are everywhere, from social networks such as Instagram, Twitter and Facebook, where the nodes are people and the links are relationships such as friendship or following, to the brain, where every node is a neuron that's connected to all of the other neurons or some of the other neurons to create consciousness. The internet is just a massive network of computers connected by fibre optic, microwave and satellite connections. The road and rail networks are just places connected by ribbons of tarmac and steel. Even ants create networks, in their case chemical pheromones, when they forage for food. And you can visualize an ecosystem as a network in which different species are connected by different relationships such as predation or mutual coexistence. And of course, recently we've seen the idea of a contact network during the pandemic, where the nodes are people and the links are the contacts that they've had with other people. And there are countless other examples of networks in the real world. And understanding how they work and how they can be used to represent and solve problems will be a very important skill for you. So here's our problem for today's lecture, and this blank worksheet is available as a PDF in the lecture materials folder. So let's just talk through the problem. So you are the mayor of this small town, and you're responsible for the upkeep of the paths around this town. And in order to keep everyone happy, you need to ensure that it's possible for anyone to walk from their house to the house of anyone else along a paved path. That is, there shouldn't be any houses that aren't on the path network. Now, you're in charge of resurfacing the paths, and you've pulled up all of the paving blocks ahead of this resurfacing, but you want to spend the least amount of money as each block is quite expensive. So each of the blocks shown is on the diagram, and each block counts as a step. So each connection between two houses has a length, which is the number of blocks. So here we have 2 blocks, so that's of length 2. Here we have 3. Here we have 1, 2, 3, 4, 5, and so on. So the question is this: how do you replace the blocks in the path network with new blocks such that it's still possible to walk between any two houses, but you use the fewest number of blocks? That is, what's the minimal network in this diagram that keeps all of the houses connected? So here's a hint. The smallest number of paving blocks you would need is 23. But the question is, how are they arranged? Because there are obviously a lot more than 23 blocks in the existing network, so some of the paths won't make it into the final network. So have a go on this blank worksheet, pause the movie and come back when you think you have an answer. So here's one possible solution, and I've coloured in all of the blocks that we'll use in the new path network. So all of these paths here are no longer used, they're no longer available, okay? And the purple paths are the paths that are available to us after the resurfacing project. Now if you count them, you'll see that there are 23. So you'll note that this new network contains far fewer blocks, but it means that some of the routes between the houses are now rather more convoluted. So as with everything in life, there's a trade-off here between cost and speed. If you want to move around more quickly, you need to be prepared to spend more money on paving more paths. However, with limited resources, you need to be prepared to take the long way around occasionally. And a lot of computer science actually asks questions such as this: how do we get an answer to our problem that satisfies a number of different constraints? So you may also have come up with this solution, which is just as short and equally valid.